Bismillahirrahmanirrahim. Hello everyone. I will talk about the classifications of the integral equation. When solving an integral equation, we use a specific method according to its kind. So, it's important for those who are interested in solving integral equation to study first its classification. Let's begin. So in this presentation, you will have to be able to define the integral equation and classify the integral equation. Then in the end, we will check if you can classify an integral equation or not by giving some examples. What's an integral equation? In mathematics, integral equations are equations in which an unknown function appears under an integral sign. And here is how we can write the general form of the integral equation. U of x equal f of x plus lambda, the integration from g of x to h of x of k of x in t u of t dt. The unknown here is u of t. K of x in t is called the kernel of the integral equation and it's a given. Lambda is called a constant parameter and it's a given too. We have f of x, g of x, and h of x are givens too. Classification 1. According to the limits of the integration g of x and h of x, we can classify the integral equation into three main kinds. 1. Fredholm integral equation. 2. Volterra integral equation. 3. Fredholm-Volterra integral equation. In Fredholm integral equations, we will notice that h of x and g of x are constants. So instead of writing h of x and g of x, we can write a and b, where a and b are constants. What about Volterra integral equation? At least one of the limits is variable, so when I look at the integral equation and find h of x or g of x is variable, then I can say that this integral equation is Volterra integral equation. And I give an example which the integration is from 0 to x. Hence, I can say that Volterra integral equation is represented. Here we are going to discuss Fredholm-Volterra integral equation. We have two integration in this form. One of them has constant limits and the other one has at least one variable limit. Classification number 2. Here we look at f of x and search for it and then see if it is existing, which is not equal to 0. Then we call this integral equation a non-homogeneous integral equation. What if we find f of x is not there, which is equal to 0? Then we call this integral equation a homogeneous integral equation. Classification number 3 discusses the linearity of the integral equation. I look at the u of t, which is the unknown of the integral equation, which is inside the integral sign. If it's linear, then you call the integral equation a linear integral equation. If u of t is not linear, then you call the integral equation a nonlinear integral equation. Classification number 4. In classification number 4, we look at the integration g of x to h of x, and we look at k of x in t. First, if we find k of x in t is unbounded at any point in the closed interval g of x h of x, then we call it singular integral equation. But what if one of the limits of the integration is equal to infinity or minus infinity? Then also our integral equation is singular integral equation. Otherwise, we call the integral equation non-singular integral equation. Classification number 5. We look at the u of x, which is outside the integration. If u of x does not appear explicitly outside the integration, then we call the integral equation a first-kind integral equation. What if we saw it? What if we find the u of x appears explicitly outside the integral equation? Then we call it a second-kind integral equation. And here is a note. Notice the appearance of u of x outside the integral equation. If it appears explicitly as u of x, then it's an integral equation, the normal one that we are working with. But if it appears as a derivative of u of x at any order, then it's called integral differential equation, and this is our note. In note number 2, we look at the kernel of the integral equation, which is denoted by k of x and t. Our k of x and t equal to 1 over x minus t raised to alpha, where alpha is between 0 and 1. Our integration from 0 to x, of course, at the cases a and b. Taking the upper limit of the integration, which is x, and substitute it in the kernel, then we get k of x and x equal to 1 over x minus x raised to alpha, which is 1 over 0. This is a singularity in the integral equation. So the cases that we are talking about in this note are singular cases. What's the difference between a and b? U of x does not appear outside the integral sign at the case a. So it's a first-kind integral equation. But b is the opposite, so it's a second-kind integral equation. After analyzing a and b, a is called generalized Appel's integral equation, but b is called weakly singular integral equation. What about the last one? The last one is a case where alpha is equal to half, and as we can see, it's a special case of a because of u of x and t that does not appear outside the integral equation, and we call it Appel's singular integral equation. Now let's solve some examples to make sure that we understand these classifications. Before solving the examples, let's have a quick review. U of x, which is outside the integral sign. If it's appearing outside the integral sign, then it's a second kind. If it's not appearing outside the integral sign, then it's a first kind. If it appears explicitly like this, then it's an integral equation. If it appears as a derivative of u of x at any order, then it's integral differential equation. About f of x, if it's equal to 0, then it's a homogeneous integral equation. If f of x is not equal to 0, then it's a non-homogeneous. When looking at k of x in t and the interval of integration h of x, g of x, we study the singularity of k of x in t over this interval. If it's singular at any point of the interval, then it's a singular integral equation. Or if h of x or g of x is equal to infinity or minus infinity, then it's singular. Singular too. Otherwise, it's a non-singular integral equation. Looking at the limits of the integration, if h of x equal to a and g of x equal to b, where a and b are constants, then it's a Fredholm integral equation. What if g of x or h of x is not equal to constant, which is mean one of them is variable? Then it's a Volterra integral equation. About u of t, which is inside the integral sign, if it's appearing linearly, then it's a linear integral equation. If it appears in a nonlinear form, then it's a nonlinear integral equation. Now let's go and solve some examples. The first example, the u of x, which is outside the integral sign, is not appearing explicitly, as is the kth derivative of u of x, then it's integral differential equation. F of x, there is no information, then if it's equal to 0, it's homogeneous. If it's not equal to 0, then it's non-homogeneous. Looking at the limits of the integration a and b, where a and b are constants, then it's a Fredholm integral equation. K of x and t, we can't specify the linearity because no information. U of t is appearing, as we can see, is linear, then it's a linear integral equation. In the second example, we can see that this is the same as above, and this is the same, and this is 2, then it's linear, and it's integral differential equation. Nothing about the homogeneous. Looking at the only difference, we find that the upper limit of the integration is variable, then it's what? It's Volterra integral equation. Okay, if there's one of the limits is variable, at least one of them is variable, then it's Volterra integral equation. Okay, let's see those. First of all, u of x, which is outside the integral equation, we can't find it. Then it's a first kind integral equation. Then this is our f of x. As we can see here, it's written explicitly, f of x. As we can see, f of x is not equal to 0. Then it's a non-homogeneous integral equation. What about the limits of the integration? They are constant, as 0 and 1 are constants. Then it's a Fredholm integral equation. Okay. Let's see now the kernel of the integral equation. Our kernel here is sine of x and t, sine x and t. As we know that we can draw the sine like this. No singular points from 0 to 1 or at any interval. So our k of x and t has no singular point on the interval from 0 to 1, and 0 and 1 are not equal to infinity or minus infinity. Then it's non-singular integral equation. u of x, which is inside the integral sign, is linear. Then it's linear integral equation. Okay, let's see the next one. U of x is appearing outside the integral sign, then it's a second kind. We have an f of x which is x, then f of x is not equal to 0, then it's a non-homogeneous. We have here the limits of the integration are constants, then it's a Fredholm integral equation. This is our kernel, k minus t. If we plug in t equal minus 1 or t equal 1 or anything in between, it will never cause a singularity. Then our k of x and t is non-singular in this interval, minus 1 and 1, and minus 1 and 1 is not equal to infinity or minus infinity. Then it's non-singular integral equation. U of t appears in a linear form, then it's linear integral equation. Let's see those examples. U of x appears outside the integral sign, then it's a second kind. F of x is equal to 1, then f of x is not equal to 0, then it's a non-homogeneous. When we look at the limits of the integration, we find that one of them is variable, then it's Volterra integral equation. Inside the integration, our kernel is 1. The 1 here is non-singular from 0 to x at any point in this interval, and in this interval none of its limits is equal to infinity or minus infinity, then it's non-singular. The 1 is not singular on this interval, and none of the limits of the integration is equal to infinity or minus infinity, then it's non-singular. Okay. Finally, u of t does not appear in a linear form because it's e raised to u of t, and we know that e is not linear, then it's non-linear integral equation. What about here? Also, u of x appears outside. Second kind. F of x not equal to 0. It's non-homogeneous. One of the limits is variable. Then it's Volterra integral equation. No singularity, because if we plug here any number where t is inside this interval, there will be no problem, no singularity, and none of the limits of the integration is equal to infinity or minus infinity, then it's non-singular. Here u of t inside the integration shows that it's a linear integral equation. Okay, let's do those. Here we have u of x does not appear outside the integral sign, then it is a first kind integral equation. F of x, no information about it. We can see that x is a variable and it's one of the limits of the integration, then it's Volterra integral equation. This is our k of x and g. As we can see here, that if we plug the x, we'll get 1 over x minus x raised to alpha, which is 1 over 0, which is a singularity. So it's singular at x. The k of x and t is singular at x, then it is singular integral equation. K of t is linear, then it's a linear integral equation. What about, is there something else? No. Then here we have u of x appears outside the integral sign, then it's a second kind. integral equation. F of x, no informations. There is x, then it's Volterra. X is a variable. It's the same kernel on the same interval, so this is singular, therefore this is singular too. Okay, u of t is showing that it's linear. Okay, now try to classify the following integral equations.